All right, welcome to lesson number 6 of the series of webinars in our water management modeling series. Today is, we've got a nice addition today. We've got Alex Edstrom with Stantec joining us to cover part of the presentation today, in which you'll see some applied aspects of simulating ponds and reservoir outflows. Before we get to that point, and before I turn the time over to Alex, I wanted to start off with some basics. And the first thing I want to do is talk about the difference between the reservoir element and the pool element, because while the pool element's been around for a while, you might be running into models that were built before that existed, and so it might be nice for you to see the difference. But also, I'm covering some other concepts that might be useful as well. What I'd like to do is start off with this this example model. That really, this is just input data for a simple pond model, and I'm going to in GoldSim here go to the categories of our elements, starting with our store category, and just walk through these different store type options that you have. So the first one is an integrator, the simplest. Now the integrator is going to be lacking some key functionality that you'll need to simulate a pond. I mean, you can do it, but it's going to be a little bit more complicated, because you have to control, you have to prevent it from hitting the physical bounds of its capacity and lower bound. So first of all, we'll start with the units. We're assuming volume, cubic meters, and then what we want to do is simulate water flowing into this pond. So this integrator, just think of it as a pond element, and we want to simulate water flowing into it. Well, I have the stochastic element that I'm using to right here to represent just simulating some random flows by grabbing some random numbers, sampling a distribution to get those random numbers. Don't worry too much about how I'm doing it. It's just a placeholder, for if you had a time series, for example, or another model that was generating this, just to simplify things. But I'm just calling it stochastic inflow because it's random, and I will just put it right into the integrator. And you see, as soon as I start typing, there it is in the list. And I can just type the tab key and complete that. Okay, so that's all we need to do to integrate or accumulate water that is flowing into the pond. And now when I do a time history result, you can see it's rising like this pretty quickly at the beginning. But what I want to do is I want to limit what we send into this pond to its capacity, which we are assuming is 2,000 cubic meters right here. So we'd want this to stop filling at this point, at about day 9 or just after day 9. Okay, so to do that, then we need to build in some logic into this integrator. Now, this is obviously not what you do with the reservoir, but let me just show what you would do if we didn't have bounds built in, and that is with an if statement. You could say if the thing we're looking at, the pond itself, which we are calling integrator 1, if it is greater than or equal to, and in our case, I mentioned 2,000 cubic meters. Well, that happens to be defined in this element over here called volume at Spillway Crest. Okay, so I'll just go ahead and type that in. Oops, volume at, I picked the wrong one. There we go. If we're at or above this, then we don't want any water to come in, so I'm going to say 0 cubic meters per day, comma, else this stochastic inflow. So what this will do is it will limit the flows coming in order to maintain an upper, a pseudo upper bound, that we kind of created ourselves. And so what you see is it hits the point, but it's actually just beyond the point of 2,000. And the reason we are beyond 2,000 here is because our time step is 1 day. And so we are only doing calculations once a day at midnight. And it turns out that we only check when we do this if statement, when you're referring to itself like this, you are referring to its, we don't want to say initial value. I mean, at time 0, it's initial value, but at each point in time, it has a value that it already had from the previous update, right? And that's its initial value on each time step. And it will grab that value and say, okay, let's do this based on that. And then by the time it updates again on the next day, it's already beyond the point that we do this calculation for. So we're never going to get it exact with this element like this. We will always cross beyond it a little bit, because we don't have we don't capture the exact point in time in which we hit this condition, unless it just turned out the math was that way, which is not. Okay, so the next thing we want to do is say, well, let's assume that we have some sort of loss factor on this pond, and we'll use a recession constant to do it. But this could be anything, any method you want. I'm just doing, for simplicity, I'm just saying that 1% of its volume is removed every day. So that's what this means. Percent per day, 1% per day. So 1% per day of this is removed every day. And so what we want to do now is, because we only have one space in here for the rate of change, we have to just keep adding an expression here and say minus, and then I'm going to say the pond volume itself multiplied by the recession constant. Okay, so now with that, we're removing at the same time as adding. So now when we run the model, we see something like this. And I want to keep this chart. So I'm going here to properties and create element, and then just call this compare store types, and then close that. Now we don't have to keep recreating that chart. And the other thing I want to do is, in addition to having a loss factor, I want to add a water demand that is based on a time series that flows only from day 20 until day 60. So the whole simulation runs for 100 days, and we're only going to have a flow of 150, or a water demand of 150 during this period between 20 and 60. So just keep in mind, I set this time series up as a constant value over the next interval. And by doing that, it allows us to set this time series up quite simply with just one value here. Because it's constant over next, it will stay at 150 until we hit the next point, which is 60 days in. Okay, so running this model, then we can see what that water demand looks like. It looks like that. Okay, so now we apply that to the integrator. And it's just, once again, it's another subtraction, like that. Now when we run this, and we look at it, we can see the water's being removed until day 60. We do have a problem though, and that is that we have a negative value. So what we need is to catch. We need some logic that says, oh, don't remove water if we're here hitting the lower bound, which in our case is 0. Okay, so that would mean in the simplistic case that we would need yet another if statement in our integrator. Obviously, you could put these equations outside in other expressions. That would probably be the smartest thing. But I'm just going to keep them in here for simplicity. So I'm going to say if, and then I'll refer to myself, integrator 1. If it's less than or equal to 0 cubic meters, then it's 0 cubic meters per day. Otherwise, it is the water demand. Okay, so that should work. And it does. Obviously, we're still crossing over. We're going down to the negative slightly because of that issue I talked about earlier. Okay, so that's okay. We could do things to fix it, but why? We don't need to. I'm just showing you that this is one of the types of stores we have. Obviously, the reservoir is going to do a much better job because it has bounds built in. In addition to that, you can separate the inflows from the outflows in these two areas. So this element is probably one that you're all familiar with if you've been doing water balance models. Whoops, that's a cubic meters. So I can add an upper bound here. I'll go ahead and put that in as the volume at the spillway crest. Same thing. Has a lower bound of 0. So having these two inputs here really adds a lot. Makes it a lot easier for us to simulate this pond. So now all I have to do is just add the inflow and add my two outflows. One is the reservoir multiplied by the loss factor plus, now I'm adding now because these are withdrawals, plus the water demand. And then because it has bounds built in, it should just work. And I'm going to add this reservoir output to the chart. We're also going to get some warning messages when we run this model, because GoldSim, it realizes that we're hitting bounds on this reservoir, and it will say, hey, because you hit the bound, like for example the upper bound, you're going to have an overflow. And where are you sending that to? You don't have any place to send it right now. And so it'll throw a warning. You'll see it. And here it is. It's actually two warnings for both for the lower bound and the upper bound. If you look at the run log, you'll see down here at the bottom, it says down here, reservoir it's overflowing, but nothing's linked to it. Also, it has outflow that's restricted, but nothing's linked to it. That's just so that it's just a way for us to make sure that, hey, by the way, you've got this this unaccounted for flow rate that you probably want to send somewhere in your model, just in case. That's why the message is there. Okay. Oh, whoops, I forgot to show you one more thing. So when we look at the chart, now you're going to see something a little bit different. First of all, we see that the red line, which is the integrator, looks a little bit different. The reason it looks different is because GoldSim has inserted extra time steps in the model, and it inserted time steps when we hit these bounds. But let me just make sure that we hit the bounds, because I started this model at a different. Yes. Okay. So in your simulation settings, if you click on the advanced, you'll see over in this area right here, it says allow unscheduled updates. So that is checked. This is by default. And this will allow GoldSim to insert time steps when you hit bounds on your reservoirs. And it will insert a time step and update all of the calculations for the entire subsystem that you're modeling. The entire model, probably, except for some exceptions if you have other subsystems, which is a bit rare. So for the most part, it's your entire model is being updated at the time you hit those bounds. So let's see exactly when we hit those bounds. We need to do that by checking this box right here. And I very often get requests or questions from our users saying things like, I have an unexpected flow, or I'm not seeing a flow that I expect, or I'm not getting a good comparison with Excel, an Excel model, and it's usually because of this. It's usually because their bounds are inserting time steps and they did not realize it, and they're not accounting for it, or they are not seeing it in their charts. Because a time history chart by default does not show the values of the inserted steps. But if we look at a tabular view, you can see at the top, first of all, it says high resolution here, indicating that, okay, we're in a mode right now where it's allowing us to see these inserted steps. And you can see there's one right there. This is the point at which we hit the upper bound. Because we hit that upper bound, GoldSim inserts a step there, and because there's a new step, that means the integrator is now catching exactly that condition of hitting that 2,000 cubic meters. Therefore, the integrator does stop there. However, as we continue forward, GoldSim is not inserting any additional time steps, and so we're going to see places where the integrator might cross again over the upper bound a little bit. It'll come back down, but it's going to be hovering above, around the upper and the lower bound. And so the integrator obviously is not really, it's going to be problematic. Now we could do things to get around it, but like I said, there's no reason to. We have the reservoir to handle these bounds. Okay, so the reservoir is quite simple, but where it starts to break down is when you have multiple outflows. For example, right here, we can't easily break these two outflows apart because they're added together in here as a total withdrawal. We would have to add another element, the allocator, outside of it in order to allocate essentially the totals of those requests and figure out how much, kind of work backwards and figure out how much of each of those requests are being sent as actual flows. It's very complicated. I mean, it's not very, but it's more complicated than what we want. That's why we added the pool element. So when you look at the pool, this one is similar to the reservoir, except it's got a few things added. First of all, that it's also looking at flows, flow units or flow outputs, and flow inputs. So we've added a new you have to put the flow unit in addition to the quantity unit. You can still put bounds in, so we could still do this. Same thing. But here's the difference. The inflows can be itemized. We only have one, so it's not that interesting. But you could itemize those, and you can itemize your outflows directly in here, which is really nice. So the first one I'm going to do is say loss. This is the one I'm calculating based on its own amount, pool times session constant. And then I'll add one more that is just my water demand. And I will just type that in directly. Now what we can do is prioritize them with this priority number. You can move them up and down. And on the output side, if we click on the output port, you can see that we have a folder here called Outflows. You open it, and these are the two outflows we just defined, which is really nice. You can also look at the total inflow as an output. So there's a lot more outputs on the pool. It's definitely recommended that you switch over. If you have a model with a reservoir, definitely switch over to the pool. And now let me add this pool element here. Okay, so we'll probably see the line on top of each other. We do. So I'm going to change the color just a little. I'll make this a little bit thicker with the dash and make this one a little bit thinner. There. Hopefully you can see that okay. So you can see that they're right on top of each other. The pool and the reservoir are working exactly the same, but the benefit here is that you can access the actual outflows very easily just by referencing these. There's the actual outflow as compared to the water demand. So we could compare this to the water demand very quickly. There's the water demand. Here's the resulting discharge from the reservoir based on what we were demanding. Okay, so that's the difference, water demand or request versus actual outflow. So a good way to build this then would be to say, oh, let's put an expression out here that's called the pumped outflow or something like that, just to keep it separate from the water demand. Something like that. And then we would just refer to pool.1 or pool1 dot, and then refer to we call it outflow one. There it is. Okay, that kind of thing. The next thing we want to consider is that instead of hitting these bounds, we can put additional logic in the model that prevents us from using those bounds at all, but instead uses them in expressions as a way to control the volume separately from, or allowing us, the modeler, to control the flow instead of having GoldSim control it with the bound. And also you would avoid inserting extra time steps. Okay, so what we could do is say, let's use a rating curve, or you could actually calculate hydraulics of, let's say, for example, an uncontrolled emergency overflow or spillway or something. And we're going to assume spillway here. And so what we want is, first of all, let's figure out how much volume of water are we above the spillway. And we can do that with a simple calculation right here that says, let's take the pool volume and subtract from that the volume at the spillway crest. Okay, so a lot of times this will be a negative number. We don't care. But what we want is a rating curve that says, okay, based on that extra volume above the spillway, we're going to say discharge a certain amount based on a linear interpolation as we rise above the spillway. So this lookup table shows the spillway or volume above the spillway in increments, and then over here on the right is the amount of flow that will be discharging based on doing a linear interpolation and looking those values up. So now what we can do is come over here to the pool and add another outflow that says, we could call this overflow or spill flow or something like that, and then just refer to the rating curve and the volume above the spillway. And so now we have a third outflow that should control the flow, the water level at the top, or at the high end. So now we can remove our upper bound because we're controlling it externally and rerun the model. And now you can see, I'm sorry, excuse me. Now we can see how we are, the blue line is the pool element. We're rising above the upper bound of 2000, but we're controlling it externally and dropping back down again We still use that hard lower bound down here, but you could do other things very easily. For example, you could have a status element that Alex will talk a little bit more about. You could do various things to control your water demand. You could turn your water demand off if the water level gets too low or starts to approach the lower bound. So you could essentially avoid all of these inserted time steps as you hit these bounds. But if in your model, in your case, if you don't have any reason to insert unscheduled time steps, then it could be that you just want to stop allowing them. And if you do that, then what that will do is every time you calculate an overflow or an outflow when you approach the bound, it's just going to calculate the average over the 24-hour period, assuming you have 24-hour or one-day time steps. That's what it will do in this case. So I would say definitely do this if you are very concerned about producing results that are compatible with an Excel model, for example, or some other tool that does not insert time steps. But if you're doing a model where you need to actually see, you have random events perhaps occurring, or failures or something, you definitely want this. But otherwise, you can just uncheck it, and then it's going to just calculate like a spreadsheet would with averages over those basic steps of one day. In this case, one day, because that's how my model's set up. But by doing that, you're not going to see a lot of difference here in the results, but what you won't see are any inserted time steps. Okay, so this kind of covers the difference between a lot of these elements, and I don't want to take any more time. I'm going to turn it over to Alex now, who's going to show you how this can be applied. But we do highly recommend that you ask us any questions if you have any at the end or also during the presentation. So I'll go ahead and turn the time over now to Alex, and I'll make you the presenter.
Sounds good. Thanks, Jason. So yeah, again, just to reintroduce myself to everybody, Alex Edstrom with Stantec, and thanks for joining and giving both Jason and I some of your time this afternoon. The example that I'm presenting today applies to a pre-feasibility study for a mine that was located in the Western United States. So I'll take some time just to introduce kind of the big picture view of the model and what I'm after in terms of the analysis, and then we'll dive into the GoldSim specific elements, the status element, how we use that to control flow rates, and depending on availability and time, if there's other questions, can feel free to look at other stuff as we have the time for it. So in terms of the overall model structure, maybe the best way to get through this is just to talk through the project example for this pre-feasibility study first. So this map shows the mine extents, and there are 5 ponds that we were interested in evaluating water levels at those ponds, and 3 of the ponds are downstream of these green outlined waste rock areas. So in developing the mine, obviously there's the pit, there's where we extract the ore that can be recovered economically, but the material that doesn't meet the required cutoff grade gets sent to these waste rock piles. And as you can imagine, geochemistry of that rock, it's very important to capture and collect that water, manage it in an appropriate way. And so for this specific example, each one of these waste rock facilities, given again, this was at a very early stage in the project, we didn't know the geochemistry, we just assumed that any water hitting this waste rock pile would then report to these downstream ponds through some sort of engineered liner or in general engineered controls. So that'll be the focus of what I talk about. But in terms of the big picture of this project, there was a need to also remove groundwater, especially at this pit that I'm circling right now. The groundwater level was too high. There's additional ore that could be recovered beneath that level. And so the dewatering process here creates some surplus water that we have to manage. And there's 2 management options. We can send that to the process facility, which is shown by this checkerboard area, or we can send that to a rapid infiltration basin where this groundwater then basically we remove it from one location, we potentially add it at a separate location, and this would be located in a place where this groundwater wouldn't have an impact on the operations over here. So the idea is, we're taking groundwater, we're returning it to groundwater, or if we need to, we can supply, the mine process with some makeup water. And then the other big thing in terms of the ponds, that water is, depending again on the geochemistry, this can't be allowed to discharge off site. This needs to be managed appropriately. So ideally, we're first using that water as much as possible in this process area, or there may be conditions, a storm event or a big snowmelt event in the case of where this site's located, where maybe there's competing needs for, or maybe there's too much water and we have to send it to some sort of emergency pond. So in terms of the structure, those are the three things that I'm allocating at the end of this model. There's the excess groundwater that I'm sending to that rapid infiltration basin. There's the total makeup to the process plant, or there's this excess water generated by the ponds that's sent to this emergency event pond. So those are the three kind of primary results that we were after. And the rest of the model is looking at, all of those different components tied together. So, each one of these kind of squares is representing a major element of the mine design that really was like its own separate report and required, pretty rigorous studies to come up with. So obviously, the climate data is a big part of any water balance model. These waste rock seepage rates were developed in a separate hydrous model for each one of those facilities outside of GoldSim. And then those results are time series, and all of these time series are aligned, and we can look at them stochastically with Monte Carlo time shifting. So in the model, all these start with year 2025, and then for the realizations that we have available, we're changing the starting year, and those are changing to hit every year of the mine schedule that we have planned, and it's 10, 11 years for this project. So we look at roughly 100 years of different historic climate data. We apply it over the 10 years of the operation, and there's some dynamic changes that are coming up, especially in the pond management that I'll show in just a second. So in terms of the overall structure, a couple things. The blue arrows are actual water flows. The red arrows are demands. So that's, water we need to make up, but the supply is coming from one of these, again, either the dewatering or the collection ponds. The gray arrows, I changed the color on those to show where there's logic being returned. So again, there's a feedback loop between, the pumping logic, and we'll discuss the status element here in a minute to get at that. And then there's also some logic being sent. Well, this logic here, we're also doing some separate pond mass balance calculations. So this isn't a water flow necessarily, but a check on the overall performance. So to get into the specifics of the pond, I'll just focus on one of these, but the structure here is modular. And maybe before I do that, you might be wondering why these boxes are red, and you can see that this is a conditional container. And the condition here is these ponds are turned on in the model depending on the mine schedule. So not to spend too much time here, but the waste rock facilities here, the pit that's being dewatered is being mined first. And so this pond needs to come online faster than these two downstream ponds. So this conditional container is just a nice way to, hard code that, I don't need to worry about the water levels in these ponds until I hit a certain point in time. And then they're magically constructed overnight, right? There's no lag time built into this in the model, but from an engineering point of view, just from a an overall systems point of view, they're not all built and put in place on the same day. So diving into just one of these examples, this particular pond, again, this is modular for each one of those 5 ponds I showed on the previous page. And there's a series of inflows that are all located on the left. And those inflows include the direct precipitation. So the ambient precip that's falling directly into this pond that I've doodled down below. There's also the runoff from the waste rock and also from native areas. We actually, for this model, we split out native versus waste rock versus reclaimed waste rock, because the goal at the end of this design is to establish vegetation, try to shed as much clean water off this as possible. So there's actually 3 different runoff calculations happening over time. And then there's also the seepage, and the seepage varies depending on if this waste rock is exposed or whether or not we've put a reclaimed cover that helps minimize how much water is going to come through. And again, any of this water that breaks through is coming from that hydrous modeling I discussed, and all of that water again is showing up at the pond. If you wanted to get more complicated, you could assume losses to the environment here that would drain back to groundwater, but that's well beyond, that's kind of wishful thinking at this stage of the project. So in terms of outflows, there's really only 2 that I had for this actual project. There was the evaporation rate directly from the pond, and then there's pumping to manage, obviously the size of this pond. If we just wanted to control this thing with evaporation, it would need to get much larger. It would need to store a lot more water. And you can see we're just limited on real estate, and that's often the case. It doesn't make sense in a lot of places to use evaporation as the only form of water management. So we knew right away we were going to need pumping systems for most of these ponds. And to do that pumping, I'll go ahead and talk about the status element now. So I've built in a couple of links, so I'm not showing you how I get there in the model. So maybe just to take a step back, again, in terms of the structure, I've kind of got this nested series of ponds that are all referenced individually. I've got my inflows, my outflow requests, which Jason just talked about, and then I'm reporting my actual outflows down here, and then within this pond container is where I've got all the individual just pond logic around operating volumes, areas, that kind of stuff. So I'm 3 levels down here, and then all of the pond pumping logic here is just in this individual container. And I'm not showing it, but I've got copy and pasted the same structure for all of those other ponds. So I'm using, again, what's really nice about GoldSim is if you can compartmentalize things and make them, modular, then it makes it a lot more efficient to set up different parts of the model. So with that in mind, we'll talk a little bit about the status element itself. And probably the easiest way to start here is I'll run this model as is, and just to keep things short, I'll run one realization for now. And what you can see is based on those inflows and outflows, outflow requests, I'm managing water levels within a couple of different bounds. And just to take a second to talk through this figure, this black line is the maximum pond storage volumes. So that would be, if you got a pond or your coffee cup in the morning, that would be the lid of your coffee cup. If you put even just a drop more water, it's going to spill over. This line down here is that's how far you want to fill the coffee cup to feel comfortable, right? So an engineering design will also, will often have, a foot of freeboard, 2 foot of freeboard, and then maybe some stormwater consideration to offset in our pond. So that's this line, kind of our indicator that, hey, you're getting too full. And then this next line, these next 3 lines are the when I have different pumps activating. So in this model, this lower blue line is a low level off switch, and this next line up is kind of my primary pump controlling operating volume. So in this example for this peak that I'm looking at here, as soon as the water level gets above this peak, I send that information to the status element, and the status element then has some additional logic attached to it that says, hey, kick the pump on. So you can see that that pump is working and it's drawing water. I'm not showing that here, but the water level here is being controlled, and there's still some water that's coming in to keep this rising, but this is actually pumping. And as we start to come down, we're still pumping until we hit this low level off switch. So it doesn't stop as soon as I hit this line, it stops when I hit this low level line. So just to show what that looks like, we'll go back to the status element. And again, working from bottom to top, as was shown on the previous figure, there's an off volume here, and you know, if you're like me, I tend to think in terms of offset distance or elevation first. So this is 3 feet above the bottom of the pond. And in this example, I'm just multiplying it by a fixed area to convert to a volume. And that gets sent to this, you know, the status element. And the important thing with the status element is we want it to trigger, this type is really important. There's a lot of different types, but in terms of a pond volume, you need to focus on and change this to an at stock test, which basically says it's tracking based on volume, not based on a change in day or a time step. And that'll help it activate at the appropriate time. So if you need to insert a time step, this stock test will let you do that, and it doesn't transition, say, from day 9 to day 10 in Jason's previous example. So again, there's 2 parts to this, and I'll just go ahead and I'll get back to edit mode here. So there's a trigger on true. So trigger to set status to true. So basically, again, as long as we exceed that that initial pumping volume, it will stay true until we come back to false, and that's that lower volume that I showed on the graph previously. So the neat thing here is you can put a bunch of these together like I did here. So I've got a low, I'm calling it a low switch and a high switch. And the thing here is these are telling us the model condition. So in GoldSim, you know, conditional elements are shown by green lines by default, so I've kept those the same. And really, this is telling me a true or a false. And so that true or false, I'm then sending to a selector element. And so here I'm saying if the pumping switch is true, the high pumping switch, so if this is set to true, I have 2 pumping rates total. I have a low at 50 gallons per minute, and I have a high pumping rate at 350. If I have, so this condition I'm putting first because I want to check if I need both pumps. If I don't need both pumps and this low switch would then be true, I can just run the lower pumping rate at 50 gallons per minute. And obviously, if both of these are false, I'm not pumping at all. So again, you can see I'm referencing these values, and really this logic is really nice. I've also got this pump tracking element. So again, if I'm saying this value is true, then I could record how many days I'm pumping. You know, you could also combine this with power equations to calculate how much energy you're using based on a single pump. You know, these status elements are pretty great for incorporating a lot of different information. So if I go, let me just go back and instead of just talking at this thing, let's actually change a few things. So let me run the model as is. And I'll just go ahead and make a copy of this. If I can find my little snipping tool, and we can look at some before and afters just to illustrate this better. So I'll put that off to the side. And let's just change this. And so the clear thing here is if I change any one of these operating levels, that's just going to set this trigger line up or down. I think we're all pretty comfortable there, but just to show, again, the influence of this low pumping rate, if I change this to say 400 gallons per minute, just to make it an extreme case, let's go ahead and run that. And go back and look at this. So now you can see just a lot more variability, a lot more on and off. And, depending on, really depending on the water demand downstream and costs of operating this pump, do you want that type of toggling? There's maybe some potential benefits to this type of behavior versus a more drawn out behavior. The other thing, we'll go ahead and go back for a second here. I changed this one back to 50. And now I'm going to just run, you can see here I was only running one realization. Again, I've got 97 years of climate data. So I'm just going to let this full thing run, and while that's going in the background, we'll come back to it in a second. But the other thing, is it going to let me move? It should let me move around. Oh, funny. Let me go ahead and actually pause that. That'll be good enough. And so, obviously there's different climate scenarios we need to take into consideration. So just to look at some of the early statistics, if it doesn't crash out. Oh, lost it. I was hoping to avoid that, but I'll bring this back up.
What exactly did you click on when that happened?
Well, I had paused the scenario, and then I went to go look at the probabilistic results as I had paused it. So I was in this element, and it just didn't like that I was trying to do a couple of things at the same time, but that's okay.
While you're in scenario mode?
Yeah, and
okay, sorry to interrupt. Keep going.
Oh, no, not at all. So let's go back to that. Let's just try to run, just show the realizations, just to show the variability. Give that a second. Oh, I need to hit run. But that's, this type of these types of elements. And another thing that I have built in that maybe can show is I also have a couple of status elements that are just tracking, if you change the area of this pond and it overtops, you can have an interrupt. But instead of interrupting the model, what I sometimes do is I'll build in the logic to track just how many days I was over, just to see how close or far away I am from actually sizing this appropriately. So, if you've only got a handful of days and it's around one event and one realization, you can hone in on that pretty quickly. So there's some nice tools you can build in to these status elements and checking the conditionality of the functions. I'll try this one more time. There we go. So you can see here, we're looking at the probability of the water stored in the pond. And most of the time, in this example, we're maintaining kind of within this lower pumping level, but occasionally we get into the high level, and I cut it off early, but there's one scenario in particular, at least with the way this model's set up, where you'll notice there's a peak here, and this peak is controlling because there's actually a large amount of native runoff area, and that's a little more watertight material than the waste rock, which is obviously, more of a chunky, potentially mixture of like gravels and sands and silty material versus the native area, which a lot of the Western United States and in a lot of mining areas in general, those native areas can be pretty exposed, shallow soils. So there's potential, when you build this pond, depending on the contributing area, or if you have any kind of upstream controls, you can potentially get runoff events in those first couple of years. But as that footprint expands, you kind of get into these interesting trade-offs between how much of this reclaimed area is going to report to the pond versus how much of the the seepage that's coming through the bottom gets there. So there's a lot of dynamic things that are happening at the same time, and the details of that, that's why mining is interesting. There's always more details to this type of work. So in terms, that's kind of the crux of what I wanted to cover there with the actual status elements, and can look at different examples here in a minute. If I change, again, I've got just a fixed area for this example. I can raise and lower that, and we can look at how that's variable. But just to kind of summarize this project, the water allocation piece of this, again, the important thing here is how much water are we sending to this event pond, because that's really only in case of emergency conditions. And you can see here, I've got a probability of what that water looks like. So there's in total, I'm looking at this as a cumulative amount, but generally, we're on the order of 10 acre feet, roughly, maybe 20 in some more extreme climate conditions. So that's information that you'd want to pass on to the engineer. You'd want to coordinate with the team that's responsible for developing these types of process facilities, or risk management in general. It's, hey, I have this potentially impacted water that I've got to route somewhere or handle somehow. And that's where the trade-offs get interesting between the amount of land that's available to make the systems bigger. Do we have to now move this waste rock pile? Do we have to push it up the hill? Again, so if nothing else, the fact that this client was willing to implement a GoldSim model right away, you can develop models that aren't quite this complex, but still get a lot of these processes to help guide your decision making. So obviously we're users on this call, but there's a lot of real value in trying to think through these relationships and how they affect overall mine water. The other thing, just to hint on, just to show the schedule. So here I'm just looking at the total percent of any of this waste rock that's mined from these different facilities. And there's different phasing that we're tracking, again, based on the mine schedule. There's makeup water demands. So this process demand is coming from a separate heap leach model. And this is kind of their typical, but you could also implement obviously probabilistic scenarios around this demand request. And that's when things get really interesting, because that's when you're really stressing the likelihood you're going to be able to meet that supply over the long term. In this case, we can, because we have that fixed kind of dewatering system, but you can imagine in other water stressed environments, getting an idea of what kind of water makeup demand is actually needed for a community, mine site, those types of questions get very interesting too. So I guess with that, rather than ramble on, maybe you can turn it over to questions, or we can do some, some what if studies with, with this model. And maybe the other thing, just to hold that thought for 1 second. So I am doing mass balance checks on each one of those. And if you haven't heard Jason mention it before, using integrators for mass balance check is definitely the way to go. It allows you to keep track of inserted time steps, especially on your outflows. And you can see, I'll just share which one of these. Well, let me go back and just run for a individual scenario. But in general, I do have a little bit of residual error, but it's overall, it's very small. If it lets me discard. Strike 2. Pull this back up.
Oh, that must be related to it being partway through a run. Interesting.
Well, that's always the case, right? As soon as you have to do anything live is when it
yeah.
Never have any problems with it until you're in front of an audience. But let's go back and just look at that for a second. So so for each one of these pond elements, you can see I've got a cumulative inflow that's tracking off this cumulative inflow. And then I've got a total outflow somewhere not shown here. And then there's also the volume in the pond itself. And I'm just collecting those calculations here. And this, I wanted to look at not just the instantaneous, the instantaneous value, but also cumulatively over the entire simulation. So I've got an integrator on that result too. Oh, it didn't save that? Interesting. Wonder if I'll get a warning. No? Okay. So you can see here, we're talking acre feet, and this is roughly what, 1 cubic foot of air, give or take. So 4 cubic feet. So pretty small overall when you're, and that's consistent across each one of these. Well, here it's a tiny bit more. Okay. I was tooting my own horn too quick there, but yeah, that covers the gist of it. Status element, if you're not already using it all the time, you probably will be soon. So
great. Thanks, Alex. I appreciate you taking the time to kind of give us a picture of what it looks like to use the concepts I always talk about, but in a real situation. And it's also nice to see how a lot of this is organized. I think it's organized very well. So, so that's good. I don't see in this case any other questions at this time, but we will wait around just a bit. I do have a question though. Was this model, did you say this model was originally built with reservoir elements before we had the pool, or was it built with the pool elements already?
This one was so I'm the original builder on this one, so I've been using pool elements from the get-go. But
okay,
I have worked with prior to version 12. I mean, I was using version 11 for a while there, and I'm probably actually still, again, it's kind of the creative thinking through GoldSim, right? There's ways you kind of train yourself to do on one version, and then there's probably better ways, and they still work, but it's hard not to get stuck sometimes on some of those old ways. So
no, that's understandable, but yeah, no, that's great that you're using them. I also like this this concept of having the conditional containers in there for the parts of the project that start up at different times. So that's pretty nice. Are you using any of the container outputs on those conditional containers? Just curious, not that you have to, but I was just curious if you were.
Yeah, and I mean, if I'm remembering correctly.
Yeah, these
Yeah,
outputs. Well, the outputs that are produced on the container itself. So like if you click on the output port of the container,
yeah, and I'm
those outputs,
fairly sure I am.
conditionality ones is what at the very top. That yeah, those. I was just curious. Um,
Oh, so I just the fact that nothing's jumping out to me, I'm probably not.
yeah, yeah. What's interesting about these sometimes, and it's probably not the case for you, but sometimes you have like when it completes, when a project completes, that it would trigger a follow-up project, the next project after that. That kind of gets more into project modeling, um, where you have um, an unknown duration
Yeah,
of a project.
right. So yeah, so when you explicitly have some sort of upstream complete triggering the start of something else, that's so
Yeah,
you would use that on at a container level?
yeah. So the container has outputs
Huh.
now. When it's conditional, yeah, the container has outputs that can trigger other the start of other events or other containers even. Um,
Hmm.
there is a question here. Someone asked, said, I've recently built a model with 65 reservoirs, so that's quite a few. Um, the reservoir
Kudos.
Oh, the reservoir matrix. Yeah, I forgot to mention this. I mentioned it in the morning session that yes, the one time the one time you should use a reservoir element instead of the pool for ponds or reservoirs is if you have a lot of them and you want to simulate it as an array, so you don't have to repeat or make copies of all the elements. The pool element is only a scalar at present. Yes, that's true. Are there any thoughts to make the pool element an optional vector? The problem, it's complicated because we have lists inside the pool. You have an inflow list. So the question would be, are all of those inflows also arrays? And then even more complicated is on the output side where you have individual flows that you're defining, and would those be arrays? Those would have to be arrays. So that you could, but we'd have to put a lot of restrictions on the data types of the requests and the inflows. They would also have to be arrays. Currently, we do not plan to do it because it is so rare that we hear of people building reservoirs as an array of reservoirs like this, and therefore, because the reservoir element allows for arrays, we would just suggest the use of a reservoir. Unfortunately, that's not so easy because um, that requires probably an additional allocator element, which cannot be used as an array. But we have a model example online in our library that is kind of the quote unquote vectorized version of the allocator. So if you need it, we can provide that, or you can go get it, and that way you could have the vector reservoir in combination with a vector allocator. So that would solve that problem. To answer that question, hopefully that answers the question. Yes. Okay. Well, we'll just see if there are any other questions here for a bit, and if not, while we're waiting, I just wanted to say thanks for joining. And if you haven't already, I recommend registering for the next lesson. Next week we'll be simulating a pump station, and the week following that will be another guest speaker talking about another type of runoff calculator. And you'll have to register for these individually to attend each one, and you can do that on our website. So it looks like we don't have any other questions, Alex. Was there anything else that you wanted to add before we close?
No, just in general, thanks for giving me the chance to present, and again, appreciate, folks hopping on and taking the time, and yeah, I guess if in general, if you have questions, I know Jason on the announcement, you put my LinkedIn contact info. If you've got project interests, that kind of thing, feel free to reach out. Or in general troubleshooting type of stuff. This is it's a great community, and post COVID, I'm looking forward to the next conference in person at some point.
Yeah, yeah, so are we. We're really looking forward to going back to normal again.
I mean, I think everybody's there, but yeah, and
Yeah,
the bar is pretty low right now, right? But
yeah. No, GoldSim does plan to. We were actually thinking of this fall, before everything all crashed and burned. But maybe once we're out of the woods, yeah, we would like to start planning again for another user conference, probably in the Seattle area again, and probably in the fall. Also, we would eventually like to have one in Australia, but that's just something we've been talking about a little bit. But anyway, we are definitely thinking about it, and when we can start planning it, we definitely will. Somebody said, really like this kind of presentation from real mine water management models. Suggest to have more. Yes, I would love to have more, and we always welcome folks like Alex to to join us and have this kind of combination of the GoldSim theory with the applied. So I agree that it's a good way to do it. Yeah. Great. Well, thank you, Alex, for taking the time. I really appreciate you doing this too. Yeah, so go ahead and if you get a chance, register for future ones, and you can look at the ones that we do have guest speakers. If those are of more interest to you, you can look at those. We'll hopefully see you next week.
And I'll just jump in a quick plug. Nick Brink, somebody I work with here at Stantec, is also going to be on a future webinar in this series too. So if you did enjoy this one, like Jason said, Nick's got some really good experience with some large operating mines. So
Yes.
while this was more on the pre-feas study, Nick's had some good work with calibrating and getting into the little bit more on the the applied data side, which I'm trying to snag away from him, but we're sharp elbows for that kind of stuff.
Yeah, and thank you for bringing that up. That's going to be lesson 9, and that's going to be covering basic tailings storage facility models. So if you're doing mine water balance modeling, it'd probably be a good one to register for. And also, by the way, we do record these presentations, and we put the video recording in our archive. So if you missed any part of it, or you want to forward this to any of your colleagues, you can do that. So with that said, we wish you all a good evening, and hopefully we'll see you next week. All right, thank you. Have a good one. Bye.